The RBMK-1000 reactor at Chernobyl Unit 4 represented a fundamentally different approach to nuclear power generation than Western pressurized water reactor designs, where Western reactors concentrated on robust containment and inherently stable thermal hydraulic behavior. The RBMK design prioritized neutron economy and operational flexibility through a distributed architecture of individual pressure tubes within a graphite moderator matrix. This design philosophy created specific information challenges that Soviet engineers addressed through sophisticated instrumentation systems rather than inherent physical constraints. The reactor's information architecture centered on indirect measurement systems that inferred critical parameters through calculated relationships between directly observable quantities. The pressurizer level indication system exemplified this approach. Rather than directly measuring coolant level within each pressure tube, physically impossible given the distributed geometry, the system calculated bulk coolant inventory from pressure differentials across multiple measurement points. Under normal single-phase flow conditions, this approach provided accurate and reliable indication of reactor thermal hydraulic state. The fundamental assumption underlying this measurement philosophy was that reactor coolant would remain in single-phase, liquid form under all credible operational conditions. Soviet thermal hydraulic analysis had demonstrated that the RBMK design maintained adequate subcooling margins during normal operation, accident scenarios involving loss of coolant, and even severe transients involving multiple equipment failures. The pressure tube geometry, with its enhanced heat transfer characteristics and multiple parallel flow paths, was specifically designed to prevent the transition to two-phase flow that could compromise measurement accuracy. This assumption became embedded throughout the reactor's control and protection systems. Automatic control logic interpreted pressure-derived level indications as absolute measures of coolant inventory. Protection system set points were calibrated assuming direct correlation between measured pressures and actual thermal hydraulic conditions. Operating procedures emphasized systematic response to parameter deviations without requiring operators to validate the physical meaning of instrumental indications under transient conditions. The RBMK design incorporated another fundamental characteristic that distinguished it from Western reactors, a positive void reactivity coefficient under certain operating conditions. While Western PWR designs exhibited negative void coefficients, meaning that steam formation would automatically reduce nuclear reaction rates, the RBMK's graphite moderated water-cooled configuration created conditions where reduced water density could increase reactivity by improving neutron moderation efficiency. Soviet designers understood this characteristic and incorporated compensating mechanisms, including a large inventory of control rods and automatic protection systems designed to counteract positive reactivity insertions. The control rod system itself embodied the RBMK's operational philosophy. Each control rod consisted of a neutron-absorbing section attached to a graphite follower. During normal operation, the graphite followers provided enhanced neutron moderation while the absorbing sections remained withdrawn. This configuration optimized neutron economy and allowed precise reactivity control during power maneuvers. The emergency shutdown system, designated AZ-5, was designed to rapidly insert all control rods simultaneously, providing immediate negative reactivity insertion sufficient to overcome any credible positive reactivity excursion. The relationship between control rod design and reactor physics created a subtle but critical vulnerability that remained theoretical until tested under specific conditions. During the initial phase of emergency rod insertion, the graphite followers would displace water in regions where they were inserted. If those regions contained significant void fractions, steam bubbles reducing water density, the displacement of remaining water by graphite could temporarily increase local reactivity before the neutron-absorbing sections achieved full insertion. Soviet analysis had calculated this effect as negligible under normal operating conditions, where adequate subcooling would prevent significant void formation. Reactor instrumentation systems were designed around the principle that accurate measurement of individual parameters would provide sufficient information for safe operation. The neutron flux monitoring system measured power distribution through multiple detectors positioned throughout the core. Thermal hydraulic instrumentation monitored coolant flow, pressure, and temperature at numerous locations. The combination of these systems was intended to provide operators with complete situational awareness of reactor state under all operational conditions. The human factors aspects of RBMK operation reflected Soviet industrial philosophy, emphasizing systematic adherence to established procedures. Operator training focused on recognizing parameter deviations and implementing prescribed responses rather than developing diagnostic reasoning capabilities. The complexity of RBMK thermal hydraulics and neutronics was considered beyond the scope of operator responsibilities. Detailed analysis was reserved for reactor physics specialists and design engineers. This approach had proven successful during years of RBMK operation across multiple units, where procedural compliance had maintained safe operation through numerous planned and unplanned transients. The integration of these design elements, indirect measurement systems, positive void coefficients, graphite follower control rods, and procedure-based operation created the RBMK's operational characteristics. Under normal conditions, this integration provided exceptional operational flexibility and efficiency. The reactor could be refueled during operation, power could be adjusted rapidly without thermal stress, and the design's inherent neutron economy provided superior fuel utilization compared to Western alternatives. However, the integration also created latent vulnerabilities that remained dormant until specific combinations of conditions arose. The measurement system's reliance on single-phase flow assumptions meant that their diagnostic capability would be compromised precisely when reactor behavior became most unstable. The positive void coefficient, normally controlled through adequate coolant flow and control rod positioning, could amplify instabilities if those control mechanisms lost effectiveness. The emergency shutdown system's temporary reactivity insertion effect, negligible under normal conditions, could become significant if implemented during void formation episodes. The regulatory framework governing RBMK operation reflected confidence in the design's inherent safety characteristics and the effectiveness of procedural controls. Safety analysis focused on loss of coolant accidents and external events, rather than operational transients that might violate the fundamental assumptions underlying the reactor's information architecture. The possibility that normal operation could create conditions where protective systems might temporarily worsen rather than improve reactor safety had not been systematically analyzed. Soviet nuclear engineering culture emphasized theoretical analysis and systematic testing of individual components and subsystems. The RBMK design had undergone extensive analysis and testing of its thermal hydraulic performance, neutronics characteristics, and control system responses. However, the integration of these systems under conditions that might violate fundamental design assumptions had received limited attention. The focus remained on component performance rather than systemic behavior under boundary conditions. The April 26, 1986 turbine test represented the fourth attempt to validate an electrical system modification designed to bridge the 40-second gap between main power loss and emergency generator startup. Previous attempts had been unsuccessful due to various technical difficulties, creating pressure to complete the validation during the scheduled maintenance outage. The test procedure required reducing reactor power and isolating steam systems to simulate main power loss conditions while measuring the electrical output from turbine generators during coast down. This test would create the specific combination of reduced power operation, minimal control rod insertion, and altered cooling flow patterns that could challenge the fundamental assumptions underlying the RBMK's information architecture. The reactor's designers and operators had no reason to suspect that following established procedures under these conditions would initiate a failure sequence that would prove the inadequacy of their most basic assumptions about reactor behavior and measurement system validity. The conditions that would prove critical on April 26, 1986, had been developing over months through the accumulation of operational decisions that individually appeared reasonable but collectively created unprecedented vulnerability. The reactor's operational state on the evening of April 25 reflected normal power plant economics and operational practices that had been refined through years of successful RBMK operation across the Soviet nuclear fleet. Unit 4 had been operating with significantly fewer control rods inserted than design specifications recommended. While safety regulations required a minimum of 15 control rods to be inserted at any given time during power operation, the actual configuration maintained only 6 to 8 rods in the inserted position. This deviation had developed gradually as operators optimized power output and fuel utilization. Each incremental rod withdrawal had been justified by immediate operational benefits and remained within the broad envelope of approved operating procedures. The reduction in control rod insertion had occurred through systematic margin erosion that remained invisible to normal oversight mechanisms. Individual rod movements were approved based on immediate neutron flux distributions and local power density measurements. The cumulative effect of multiple rod withdrawals over extended periods was not systematically tracked or analyzed. Reactor physics calculations performed for individual operational decisions did not account for the integrated effect of minimal rod insertion combined with other operational variables that might arise during transient conditions. This operational configuration created heightened sensitivity to reactivity changes. With minimal control rod insertion, the reactor's neutron multiplication factor operated closer to critical than normal, meaning that small changes in reactivity could produce larger changes in power output than anticipated. The reduced control rod inventory also meant that automatic control systems had less negative reactivity available for compensating positive reactivity insertions from other sources. The human factors environment at Chernobyl Unit 4 reflected standard Soviet industrial practices, emphasizing systematic compliance with established procedures rather than independent diagnostic analysis. Operator training focused extensively on recognizing specified parameter combinations and implementing prescribed responses. The complexity of RBMK neutronics and thermal hydraulics was considered beyond operator responsibilities. Detailed system analysis was reserved for specialists who were not present in the control room during routine operations. Shift communication practices had evolved to emphasize continuity of planned operations rather than comprehensive situation assessment. When the day shift briefed the night shift on April 25th, the focus centered on completing the turbine test that had been postponed from the previous day due to electrical grid requirements. The briefing covered procedural steps and expected parameter ranges but did not include systematic review of reactor configuration, control rod positioning, or potential interactions between test conditions and existing operational state. The decision to proceed with the turbine test during the night shift reflected normal industrial pressure to complete scheduled maintenance activities during planned outages. Delaying the test would require extending the outage period, with significant economic consequences and potential impacts on electrical grid operations. The test procedure itself had been reviewed and approved through normal channels, and similar tests had been performed successfully on other RBMK units without incident. Alexander Akimov, the shift supervisor, and Leonid Toptunov, the reactor operator, were both experienced personnel familiar with RBMK operation and the specific test procedure. Their training emphasized procedural adherence and systematic response to parameter deviations. Both had performed similar tests during their careers and understood the electrical systems being validated. Neither had received training in the theoretical aspects of reactor physics that would become critical during the subsequent event. The test procedure required reducing reactor power to between 700 and 1,000 megawatts thermal, then isolating steam systems to simulate loss of main electrical power while measuring turbine generator performance during coastdown. This power reduction would be achieved through control rod insertion and reduced coolant flow, creating thermal hydraulic conditions different from normal full power operation, but well within the analyzed operational envelope. Reactor protection systems were designed and calibrated based on assumptions about normal operational practices, including adequate control rod insertion and standard cooling configurations. The protection system logic incorporated automatic responses to parameter deviations that could indicate developing problems. But these responses assumed that fundamental design assumptions about coolant behavior and reactivity control remained valid. The April 26 test would involve operating reactor cooling pumps in an asymmetric configuration, with 4 pumps powered by turbine generators and 4 pumps powered by the electrical grid. This configuration was necessary to simulate the electrical conditions being tested, but it created coolant flow patterns that differed from those used in normal operation or analyzed accident scenarios. The asymmetric pump operation would create flow distribution differences that were not monitored by existing instrumentation systems. Soviet reactor operations philosophy emphasized centralized technical authority and systematic compliance with approved procedures. Operators were trained to implement prescribed responses to observed conditions rather than to develop independent interpretations of reactor behavior. This approach had proven successful across years of RBMK operation, where adherence to procedures had maintained safe operation through numerous planned and unplanned transients. The regulatory oversight system focused on procedural compliance and component performance rather than systematic analysis of integrated system behavior under boundary conditions. Safety reviews examined whether operations remained within approved procedures and whether individual systems functioned as designed. The possibility that procedurally compliant operations might create conditions where protective systems could temporarily worsen rather than improve safety had not been systematically considered. Training programs for RBMK operators emphasized pattern recognition and procedural implementation rather than fundamental understanding of reactor physics and thermal hydraulics. This approach reflected Soviet industrial philosophy that complex technical analysis should be performed by specialists rather than operational personnel. Operators were trained to recognize parameter combinations that indicated specific conditions and to implement appropriate responses without necessarily understanding the underlying physical processes. The control room design and instrumentation layout reflected this operational philosophy. Parameters were grouped according to functional systems rather than causal relationships. Operators monitored neutron flux, coolant flow, pressure, and temperature through separate instrument panels without integrated displays that might reveal emerging patterns or developing instabilities. The information architecture assumed that individual parameter monitoring would provide sufficient situational awareness for safe operation. Emergency response procedures were designed around rapidly developing accidents such as loss of coolant events or external emergencies rather than slowly developing operational transients. The emergency shutdown system was intended for immediate implementation when parameter deviations exceeded specified limits, without requiring detailed diagnosis of underlying causes. This approach emphasized rapid protective action rather than situation assessment. The organizational culture at Chernobyl reflected broader Soviet industrial practices emphasizing plan fulfillment and technical achievement. Completing the turbine test represented both a technical objective and a demonstration of operational competence. The pressure to complete scheduled tasks during planned outages was reinforced by economic considerations and professional expectations that had been internalized throughout the operational organization. Communication systems between the control room and engineering support emphasized procedural compliance rather than technical consultation. Engineering specialists were available for consultation during complex operations, but the normal expectation was that trained operators could manage routine procedures independently. The turbine test was considered a routine electrical system validation that did not require specialized reactor physics expertise. Documentation practices focused on recording procedural compliance and parameter values rather than analyzing underlying trends or developing conditions. Operational logs captured required readings and completed procedural steps, but did not systematically track cumulative changes in reactor configuration or evolving relationships between operational variables. The integration of these human factors elements, minimal control rod insertion, procedural emphasis, shift communication practices, organizational pressure, and information architecture created conditions where the reactor's physical vulnerabilities would be tested under circumstances that appeared routine to operating personnel. The operators would implement correct procedures based on accurate instrument readings while unknowingly committing the reactor to conditions where normal protective measures would prove inadequate or counterproductive. At 1:23:04 on April 26, 1986, the turbine test commenced under conditions that deviated significantly from the prescribed procedure, but remained within the broad envelope of approved operations. The reactor was operating at approximately 200 megawatts thermal power, rather than the specified 700 to 1,000 megawatts, a reduction that had occurred during the previous day's power decrease and had been accepted as adequate for completing the electrical validation. This power level represented the lower boundary of stable RBMK operation, but remained within analyzed operational limits. The initiation of the test required isolating steam flow to the turbine generators to simulate main power loss conditions. This isolation was accomplished through systematic closure of steam isolation valves, redirecting steam flow through bypass systems to the condensers. The procedure was familiar to operating personnel and had been performed successfully during previous tests. However, the combination of reduced power operation and steam isolation created thermal hydraulic conditions that had not been systematically analyzed or experienced during normal operation. The steam isolation procedure reduced the thermal load on the reactor cooling system while maintaining coolant flow through the core. Under normal power operation, steam removal provided the primary mechanism for heat removal from the reactor coolant system. With steam isolation, heat removal shifted entirely to the condenser systems through the main coolant circulation pumps. This change in heat removal patterns created subtle but significant alterations in coolant temperature distribution throughout the reactor core. Simultaneously, the test procedure required transitioning 4 of the 8 main circulation pumps from electrical grid power to turbine generator power. This transition was necessary to simulate the electrical conditions being validated, the ability of turbine generators to provide power during the 40-second gap before emergency generators achieved full operation. The pump transition proceeded normally, but it created an asymmetric cooling configuration that differed from both normal operation and analyzed emergency scenarios. The asymmetric pump configuration resulted in uneven coolant flow distribution that was not detected by the reactor's instrumentation systems. The monitoring systems measured bulk flow rates and average temperatures rather than local flow patterns within individual pressure tubes. Under normal operating conditions, this approach provided adequate monitoring capability since flow distribution remained relatively uniform. However, the combination of reduced power and asymmetric pumping created local variations that remained invisible to operating personnel. Within the first 30 seconds of the test, subtle changes in neutron flux distribution began developing in response to the altered thermal hydraulic conditions. These changes represented the initial stages of void formation in regions where reduced coolant flow coincided with residual heat generation. The void formation was microscopic initially, individual steam bubbles forming and collapsing within the coolant channels, but sufficient to begin affecting local neutron moderation. The reactor's positive void coefficient meant that any reduction in water density would tend to increase neutron multiplication in the affected regions. Under normal operating conditions, this effect was controlled through adequate coolant subcooling and control rod positioning. However, the minimal control rod insertion and reduced power operation created conditions where small void fractions could produce measurable reactivity increases. At 1:23:40, 36 seconds after test initiation, Leonid Toptunov observed a power increase of approximately 10 to 15% on the neutron flux monitoring instruments. This increase was gradual rather than sudden, developing over several seconds in a pattern that suggested systematic rather than random variation. The increase appeared on multiple detectors, indicating a real change in reactor neutronics rather than instrument malfunction. Toptunov's observation of power increase represented the first indication that reactor behavior was diverging from expected patterns. According to theoretical analysis and previous test experience, reactor power should have remained stable or decreased slightly during the early phases of the test. The observed increase suggested that reactivity was being added to the system from an unidentified source. The power increase pattern was consistent with positive reactivity insertion from void formation, but this mechanism was not immediately apparent to operating personnel. The reactor's instrumentation systems provided no direct indication of void fraction or local coolant conditions within individual pressure tubes. Operators relied on bulk measurements of flow, pressure, and temperature, which remained within expected ranges despite the developing local variations. Akimov and Toptunov interpreted the power increase according to their training and experience, which emphasized systematic response to parameter deviations rather than diagnostic analysis of underlying causes. The observed increase remained within operational limits and did not trigger automatic protection system responses. However, the trend suggested developing instability that required corrective action to prevent further deterioration. The decision-making process in the control room reflected established practices for managing unexpected parameter variations during testing. The primary consideration was maintaining reactor stability while completing the test objectives. Secondary considerations included avoiding unnecessary reactor trips that would require extended recovery periods and complicate the electrical validation being performed. At 1:23:43, 39 seconds after test initiation, Akimov ordered activation of the emergency shutdown system, AZ-5, in response to the continuing power increase. This decision represented correct implementation of emergency procedures when reactor parameters deviated from expected values during testing. The AZ-5 system was designed to provide immediate negative reactivity insertion through rapid insertion of all control rods simultaneously. The AZ-5 activation initiated automatic insertion of control rods throughout the reactor core. Under normal conditions, this action would provide immediate reduction in neutron multiplication and stabilization of reactor power within seconds. The system had functioned reliably during previous emergency shutdowns and represented the ultimate protective measure for maintaining reactor safety during any abnormal condition. However, the specific conditions existing at the time of AZ-5 activation created an unprecedented situation where the emergency shutdown system temporarily increased rather than decreased reactor reactivity. The control rod design, with graphite followers attached to neutron-absorbing sections, meant that initial rod insertion displaced water in regions where void formation was already developing. The displacement of remaining water by graphite followers in partially voided regions provided additional positive reactivity insertion that overwhelmed the negative reactivity from the neutron-absorbing sections during the first seconds of rod insertion. This effect had been calculated as negligible under normal operating conditions, where adequate coolant subcooling would prevent significant void formation. However, the minimal control rod insertion and altered cooling patterns had created conditions where this effect became significant. The reactor physics calculations that had validated the control rod design assumed single-phase coolant flow throughout the insertion process. Under two-phase flow conditions, where steam bubbles occupied significant volume fractions within the coolant channels, the displacement of remaining water by graphite followers provided more positive reactivity than anticipated. The effect was temporary, lasting only until the neutron-absorbing sections achieved sufficient insertion depth, but proved sufficient to accelerate rather than control the developing excursion. Within 4 seconds of AZ-5 activation, multiple indicators suggested that reactor behavior was becoming increasingly unstable. Neutron flux readings increased rapidly rather than decreasing as expected. Coolant flow indicators showed developing variations suggesting two-phase flow behavior. Pressure measurements began fluctuating in patterns consistent with steam formation and structural stress. The operator's situational awareness became increasingly compromised as the reactor's behavior diverged from all previous experience and training. The instrumentation systems continued providing readings, but those readings represented conditions for which the operators had no interpretive framework. Emergency procedures assumed that AZ-5 activation would stabilize any abnormal condition, but the observed parameters suggested continuing deterioration despite implementation of the ultimate protective measure. The reactor protection systems, designed to respond automatically to specific parameter combinations, began reaching their activation set points as reactor conditions exceeded analyzed operational envelopes. However, these systems were calibrated based on assumptions about normal thermal hydraulic behavior that no longer applied. Automatic protective actions, intended to mitigate developing problems, proved ineffective or counterproductive under the unprecedented physical conditions developing within the reactor core. at 1:23:47, 43 seconds after test initiation, and 4 seconds after AZ-5 activation, the first explosion occurred within the reactor core. The explosion represented catastrophic failure of the reactor's pressure boundary, caused by steam pressure that exceeded the design capabilities of the pressure tube systems. The explosion occurred despite full activation of protective systems and correct implementation of emergency procedures by operating personnel. The destruction of Reactor Unit 4 occurred within a time frame that precluded human intervention and challenged fundamental understanding of reactor physics under extreme conditions. Post-accident forensic analysis, combining physical evidence examination, computer modeling, and isotopic analysis of debris samples, reconstructed a failure sequence that demonstrated how rapidly nuclear reactor systems could transition from controlled operation to catastrophic destruction when protective mechanisms proved inadequate for the physical conditions that developed. The 4-second interval between AZ-5 activation at 1:23:43 and the first explosion at 1:23:47 represented one of the most intensively analyzed periods in nuclear engineering history. During this brief time frame, reactor power increased from approximately 200 megawatts thermal to levels exceeding 100 times normal full power operation, estimated at 20,000 megawatts thermal or higher, based on subsequent isotopic analysis of fission-product ratios found in debris samples. The power excursion began with accelerated void formation in regions where coolant flow had been reduced by the asymmetric pump configuration and steam isolation procedures. Initial void fractions of approximately 5% in localized areas increased to 40 to 60% within seconds as positive reactivity feedback overwhelmed the negative reactivity insertion from control rod absorption sections. The transition from controlled nucleate boiling to departure from nucleate boiling occurred virtually instantaneously once critical heat flux conditions were exceeded. Detailed thermal hydraulic analysis of debris patterns and structural deformation provided evidence for the sequence of physical processes during the excursion. Initial steam formation occurred in pressure tubes where power density remained relatively high despite overall power reduction. These tubes experienced local coolant flow reductions due to the asymmetric pumping configuration, creating conditions where heat removal capability was marginal relative to heat generation rates. The positive void reactivity coefficient, calculated at approximately 0.03% reactivity per percent void fraction under the existing conditions, meant that each increment of steam formation added positive reactivity that promoted additional steam formation. This self-reinforcing process accelerated once void fractions exceeded approximately 10%, creating feedback rates that exceeded the capability of control systems to provide compensating negative reactivity. Control rod insertion rates, designed for normal reactor conditions, proved inadequate for the rapidly changing neutron flux distribution. The control rod drive mechanisms operated at fixed insertion speeds of approximately 0.4 meters per second, which would require 25 to 30 seconds for full insertion from the withdrawn position. However, the developing power excursion created thermal conditions that caused structural deformation of rod guide tubes within the first few seconds, mechanically preventing full rod insertion. Forensic examination of control rod positions after the accident revealed that most rods achieved only 2 to 2.5 meters of insertion before becoming mechanically bound by structural distortion. This partial insertion depth was insufficient to provide the negative reactivity required to control the excursion, even without considering the temporary, positive reactivity contribution from graphite follower water displacement in voided regions. The graphite follower effect, which had been calculated as negligible under normal operating conditions, became significant under the two-phase flow conditions that developed during the excursion. Each graphite follower that displaced water in partially voided pressure tubes provided approximately 0.02 to 0.03% positive reactivity during the initial insertion phase. With multiple control rods inserting simultaneously, The cumulative effect provided sufficient positive reactivity to accelerate rather than control the power increase during the critical first seconds of emergency shutdown. Steam pressure buildup within individual pressure tubes reached levels far exceeding design specifications as heat generation rates overwhelmed heat removal capability. Design pressure for RBMK pressure tubes was approximately 10 megapascals, based on thermal hydraulic analysis of credible accident scenarios. However, forensic analysis of tube deformation patterns indicated peak pressures reaching 20 to 25 megapascals, sufficient to cause catastrophic failure of pressure tube assemblies. The pressure tube failure mechanism involved rapid expansion of steam-water mixtures as heat addition rates exceeded the capability of relief systems to maintain pressure equilibrium. Individual pressure tubes began rupturing as internal pressure exceeded structural capabilities, creating additional steam release that further reduced system pressure and promoted additional void formation throughout the reactor core. Neutron flux measurements recorded by reactor protection systems during the final seconds provided evidence for the spatial and temporal development of the power excursion. Multiple detectors showed coordinated increases indicating core-wide rather than localized flux increases. The pattern suggested that positive reactivity insertion was occurring faster than neutron flux could equilibrate, creating conditions where local power densities reached levels sufficient to cause immediate fuel failure. Fuel temperature calculations based on fission product release ratios indicated peak temperatures exceeding 2,600 degrees Celsius in regions where power density reached maximum values. These temperatures far exceeded the melting point of uranium dioxide fuel, approximately 2,800 degrees Celsius, and approached levels where fuel-cladding chemical reactions would proceed rapidly. Zirconium steam reactions at these temperatures produced significant hydrogen gas generation, creating additional pressure loading on already stressed containment systems. The first explosion at 12347 resulted from steam pressure exceeding the mechanical capabilities of the reactor pressure vessel and core structure. Acoustic analysis of seismic records indicated a pressure pulse consistent with rapid steam expansion following catastrophic pressure boundary failure. The explosion scattered reactor fuel and graphite moderator throughout the reactor building, destroying the reactor core geometry and terminating the nuclear chain reaction through fuel dispersal. Approximately 2 to 3 seconds after the first explosion, a second explosion occurred with characteristics consistent with hydrogen combustion. The hydrogen had been generated through high-temperature reactions between steam and zirconium fuel cladding during the brief period of extreme fuel temperatures. The hydrogen explosion provided additional destructive energy that completed the destruction of reactor building structures and projected radioactive debris beyond the immediate reactor site. Physical evidence from debris distribution patterns confirmed the rapid progression from controlled operation to complete destruction. Fuel fragments were found throughout the reactor building and surrounding area, with particle size distributions indicating extremely rapid temperature increases and mechanical forces sufficient to fragment ceramic fuel pellets. Graphite moderator blocks were displaced distances of hundreds of meters, requiring explosion energies far exceeding any credible chemical process except hydrogen combustion. Isotopic analysis of fuel samples provided definitive evidence for the magnitude and duration of the power excursion. Fission product ratios indicated neutron flux levels consistent with power levels 50 to 100 times normal full power operation. The isotopic signatures also confirmed that the excursion duration was brief, lasting only seconds rather than minutes, consistent with the acoustic and seismic evidence for rapid progression from power increase to explosive destruction. Control rod forensic examination revealed the mechanical binding mechanism that prevented effective reactivity control during the excursion. Rod guide tube deformation was consistent with thermal expansion rates that would be expected from the calculated temperature increases. The deformation patterns indicated that mechanical binding occurred early in the insertion process, when positive reactivity addition was most critical for controlling the developing excursion. Structural analysis of pressure tube failures provided evidence for the pressure levels and failure mechanisms that terminated reactor operation. Tube deformation patterns were consistent with internal pressures exceeding yield strength by factors of 2 to 3. The failure locations and orientations indicated that pressure loading was primarily internal rather than external, confirming that steam generation within individual tubes created the destructive forces rather than external explosion effects. Radioactive contamination patterns in the immediate reactor area provided evidence for the volatilization and transport mechanisms that dispersed reactor materials following the explosions. Volatile fission products such as iodine and cesium were found at distances indicating high temperature release and atmospheric transport. Refractory materials such as plutonium and strontium showed more limited dispersal, consistent with mechanical fragmentation rather than volatilization. The physical evidence conclusively demonstrated that reactor destruction resulted from positive reactivity feedback that overwhelmed control system capability under conditions that developed during normal procedural compliance. The failure sequence proved that emergency shutdown systems could temporarily worsen rather than improve reactor safety when implemented under specific thermal-hydraulic conditions that violated fundamental design assumptions about coolant behavior. The immediate aftermath of the reactor explosions presented emergency response personnel with conditions unprecedented in nuclear power plant operations. The destruction of Unit 4's reactor building and core structure created an open-air nuclear fire with massive radiation releases, challenging every aspect of conventional emergency response protocols. The initial response decisions were complicated by systematic underestimation of the accident's severity, caused by radiation monitoring systems that were overwhelmed by actual conditions. The plant's radiation monitoring instruments had been designed for measuring radiation levels during normal operations and credible accident scenarios involving intact reactor cores. The highest reading portable dosimeters available to emergency response teams measured maximum radiation levels of 3.6 roentgens per hour, a level considered extremely hazardous but manageable for emergency operations. However, actual radiation levels in the immediate reactor area exceeded 20,000 roentgens per hour, levels that would prove lethal within minutes of exposure. This systematic underestimation of radiation conditions led plant management to initially conclude that the reactor core remained largely intact and that conventional emergency cooling procedures should be implemented. The decision to activate emergency core cooling systems represented standard nuclear plant emergency response, based on the assumption that reactor fuel geometry remained essentially normal despite the obvious building damage. This assessment proved catastrophically incorrect, but it reflected rational decision-making based on the limited and misleading information available to plant management. Emergency core cooling system activation involved pumping large volumes of water into the destroyed reactor space in an attempt to cool fuel that was assumed to be in approximately normal geometric configuration. However, the actual condition involved reactor fuel scattered throughout the reactor building, much of it burning in direct contact with atmospheric oxygen. The introduction of water onto burning nuclear fuel created several additional hazards that had not been anticipated in emergency planning. Water contact with the high-temperature fuel fragments generated massive steam production that carried additional radioactive particles into the atmosphere. More critically, the steam generation created hydrogen gas through continuing chemical reactions between steam and metallic components at elevated temperatures. This hydrogen presented significant explosion hazards and contributed to the atmospheric transport of radioactive contamination over much larger areas than would have occurred from the direct explosion effects alone. The injection of water into the reactor area also created concerns about criticality control, the possibility that scattered fissile material could achieve a new critical configuration if moderated by water. Nuclear fuel in its normal geometric arrangement is designed to prevent criticality when flooded with water, but fuel scattered in random configurations could potentially achieve critical mass if sufficient moderation and neutron reflection were provided by surrounding water and structural materials. 24 hours after the initial explosions, helicopter operations commenced to drop neutron-absorbing materials directly onto the burning reactor core. These operations involved flying sorties at altitudes of 50 to 100 meters directly over the destroyed reactor, exposing flight crews to radiation levels that delivered annual occupational dose limits during individual flights. The helicopter crews received minimal protection from aircraft structures and were essentially flying through radioactive smoke plumes while attempting to deliver materials with sufficient accuracy to affect the burning fuel. The materials dropped from helicopters included boron carbide for neutron absorption, sand for heat absorption and fire suppression, and lead for radiation shielding and additional thermal mass. Approximately 5,000 tons of materials were dropped during the initial helicopter operations, representing a massive effort to control the nuclear fire through direct intervention. However, the effectiveness of these operations remained uncertain, since there was no reliable method for assessing their impact on fuel temperature or radiation release rates. Concurrent with the helicopter operations, plant personnel were attempting to address secondary hazards that had developed in the reactor building basement areas. The emergency core cooling water that had been pumped into the reactor space was accumulating in basement rooms that also contained electrical systems essential for continued plant operation. The flooded basement areas exhibited extremely high radiation levels, exceeding 1,000 roentgens per hour, that precluded normal maintenance or inspection activities. Of particular concern was the possibility that molten reactor fuel could burn through the reactor building foundation and contact the accumulated water in basement areas. Such contact could create a steam explosion of sufficient magnitude to damage adjacent reactor units that remained in operation. Additionally, the molten fuel could potentially reach groundwater systems, creating long-term contamination of water supplies over large geographic areas. 3 plant volunteers, Alexei Ananenko, Valery Bespalov, and Boris Baranov, undertook a mission to manually operate valves that would drain the flooded basement areas. This operation required entering basement spaces with radiation levels exceeding 1,000 roentgens per hour and working in darkness while wearing bulky protective equipment and breathing apparatus. The valve operation was completed successfully, preventing the steam explosion scenario, but all 3 individuals received radiation exposures that would prove fatal within weeks. Engineering analysis of the fuel behavior suggested that the burning reactor materials would eventually burn through the concrete reactor foundation, unless additional heat removal measures were implemented. A plan was developed to excavate tunnels beneath the reactor foundation and install liquid nitrogen cooling systems to prevent foundation penetration. This tunneling operation required miners to work in shifts with exposure times limited to 10 to 15 minutes due to radiation levels in the excavation areas. The tunneling operation proceeded around the clock for several weeks, with hundreds of miners participating in the excavation and cooling system installation. Each worker's exposure was carefully monitored and limited, but the cumulative radiation exposure to the mining workforce was enormous. The liquid nitrogen cooling system was eventually installed and operated successfully, preventing foundation penetration and groundwater contamination, but at considerable human cost. Approximately 6 months after the accident, construction began on a massive containment structure, eventually known as the sarcophagus, designed to completely enclose the destroyed reactor building and provide long-term containment of radioactive materials. This construction project required over 200,000 workers operating in extremely hazardous conditions, with exposure times strictly limited to prevent excessive radiation doses. The sarcophagus construction involved assembling steel and concrete structures around and over the destroyed reactor building while maintaining radiation exposure controls for the construction workforce. Workers in the highest radiation areas were limited to exposure times of 15 to 20 minutes per shift, requiring enormous numbers of personnel to complete even simple construction tasks. The logistics of managing such large numbers of workers while maintaining exposure controls represented an unprecedented industrial challenge. Throughout the stabilization efforts, fundamental uncertainties persisted about the actual condition of reactor fuel and the effectiveness of various mitigation measures. Radiation levels prevented direct observation of fuel conditions, and remote monitoring systems had been destroyed in the initial explosions. Decision-making necessarily proceeded based on theoretical calculations and limited indirect evidence rather than direct observation of actual conditions. The international nuclear engineering community provided technical assistance and consultation during the stabilization phase, but but the unprecedented nature of the accident meant that established emergency response protocols provided limited guidance. Many decisions required extrapolation from theoretical analysis or adaptation of techniques developed for other industrial emergencies to nuclear conditions for which they had not been designed. Regional evacuation procedures, initially implemented for a 30-kilometer radius around the plant, were expanded as atmospheric monitoring revealed contamination patterns that extended far beyond the initial evacuation zone. Approximately 100,000 residents were relocated during the initial evacuation, with additional relocations occurring over subsequent months as contamination assessment continued. Agricultural restrictions were implemented over vast areas where radioactive fallout had contaminated food production systems. Restrictions on milk consumption, vegetable harvesting, and livestock grazing affected millions of people across multiple countries as atmospheric contamination spread, according to weather patterns that could not be predicted or controlled. The long-term environmental monitoring and cleanup operations would continue for decades, involving thousands of additional personnel and activities ranging from decontamination of buildings and equipment to environmental sampling and analysis. The scope of these operations far exceeded anything previously anticipated in nuclear emergency planning and required development of new techniques and procedures for managing large-scale radioactive contamination. Each phase of the stabilization efforts revealed additional aspects of the accident that had not been anticipated in emergency planning. The systematic underestimation of radiation levels, the unexpected secondary chemical reactions, the logistics challenges of managing large workforces in contaminated areas, and the long-term environmental consequences all demonstrated that existing nuclear emergency frameworks had been developed for much more limited accident scenarios than actually occurred. The forensic investigation of the Chernobyl accident ultimately provided the most comprehensive analysis of nuclear reactor destruction ever assembled, combining physical evidence collection, isotopic analysis, computer modeling, and international technical cooperation to reconstruct both the immediate failure sequence and the underlying systemic vulnerabilities that made such destruction possible. The investigation's findings fundamentally challenged assumptions about nuclear safety that had guided reactor design and operation for decades. Physical evidence collection began within months of the accident, as radiation levels decreased sufficiently to permit systematic examination of reactor debris. The distribution patterns of fuel fragments, structural materials, and fission products throughout the reactor building and surrounding area provided crucial evidence for reconstructing the explosion sequence and the thermal conditions that had existed during the final seconds of reactor operation. Fuel assembly debris analysis revealed information about local power densities, temperature distributions, and the timing of structural failure that could not have been obtained through any other method. Individual fuel pellets showed melting patterns consistent with peak temperatures exceeding 2,600 degrees Celsius, confirming theoretical calculations about the magnitude of the power excursion. The size distribution of fuel fragments indicated extremely rapid temperature increases that caused thermal shock fracture of ceramic materials. Isotopic analysis of fuel samples provided definitive evidence for the neutron flux levels and power densities that had been achieved during the accident sequence. Different radioactive isotopes are produced at different rates depending on neutron flux intensity and duration. By analyzing the ratios of various isotopes in fuel samples, investigators could calculate local neutron flux levels and confirm that power levels had reached 50 to 100 times normal full power operation in localized regions of the reactor core. The isotopic evidence also confirmed the brief duration of the power excursion, lasting only seconds rather than minutes. Short-lived isotopes with half-lives of seconds to minutes provided evidence for the timing of peak neutron flux, while longer-lived isotopes confirmed the integrated neutron exposure over the entire event sequence. This isotopic chronometry provided objective evidence for the rapid progression from power increase to explosive destruction. Metallurgical examination of control rod components recovered from the debris provided crucial evidence for the mechanism that prevented effective reactivity control during the accident. Rod guide tube deformation patterns were consistent with thermal expansion rates calculated from the observed temperature increases. The deformation occurred early in the rod insertion process, confirming that mechanical binding prevented adequate negative reactivity insertion when it was most needed. Analysis of the control rod positions at the time of binding confirmed that most rods achieved only 2 to 2.5 meters of insertion before becoming mechanically constrained. This insertion depth was insufficient to overcome the positive reactivity being added by void formation and graphite follower water displacement. The forensic evidence proved that the emergency shutdown system had lost its protective effectiveness under the specific conditions that developed during the accident. Structural analysis of pressure tube failures provided evidence for the internal pressure levels that caused catastrophic failure of the reactor pressure boundary. The deformation patterns in pressure tube assemblies were consistent with internal pressures reaching 20 to 25 megapascals, more than double the design pressure of 10 megapascals. These pressure levels confirmed theoretical calculations about steam generation rates during the power excursion. Chemical analysis of concrete and metal structures provided evidence for the peak temperatures and chemical reactions that occurred during and after the explosions. Concrete decomposition products indicated temperatures exceeding 1,200 degrees Celsius in areas where reactor fuel had come to rest. Metal oxidation patterns revealed the atmospheric conditions and temperature profiles that existed during the fire phase of the accident. The formation of corium, a mixture of molten reactor fuel, structural metals, and concrete, provided unique evidence for the high-temperature processes that continued after the initial explosions. Corium samples showed complex mineral phases that could only form under specific temperature and chemical conditions. Analysis of these phases confirmed peak temperatures exceeding 2,600 degrees Celsius and provided evidence for the chemical interactions between reactor fuel and structural materials. Radioactive contamination distribution patterns provided evidence for the volatilization and atmospheric transport mechanisms that dispersed reactor materials over large geographic areas. Volatile fission products such as iodine-131 and cesium-137 were found at distances indicating high-temperature release and long-range atmospheric transport. The spatial distribution patterns confirmed theoretical models for atmospheric dispersion under the meteorological conditions that existed during and after the accident. Environmental monitoring data collected over years following the accident provided evidence for long-term material transport and biological uptake mechanisms. Radioactive materials were found to migrate through soil and groundwater systems at rates that had not been anticipated in environmental impact assessments. Biological concentration of radioactive materials in plants and animals revealed pathways for human exposure that had received limited attention in safety analyses. International cooperation in the forensic investigation involved technical teams from multiple countries with expertise in reactor physics, materials science, atmospheric transport, and environmental contamination. This cooperation provided access to analytical capabilities and theoretical expertise that would not have been available to any single national program. The international effort also ensured that investigation findings would be subjected to rigorous peer review and independent verification. The forensic evidence definitively established that reactor destruction had resulted from positive reactivity feedback that overwhelmed control system capability, rather than from equipment failures or procedural violations. Every major system had functioned as designed. Instrumentation provided accurate readings, protective systems activated correctly, and operators implemented appropriate procedures, yet the integrated system behavior produced catastrophic failure when fundamental design assumptions proved invalid under specific operating conditions. The investigation revealed that the RBMK reactor's information architecture had created a systematic vulnerability where technically accurate instrument readings could provide diagnostically misleading information about reactor safety margins. The pressure-derived level indication system continued to show normal coolant inventory even as two-phase flow conditions developed that compromised both heat removal capability and reactivity control effectiveness. Analysis of the emergency shutdown system behavior demonstrated that protective measures designed for normal conditions could temporarily worsen reactor safety when implemented under specific thermal hydraulic conditions. The graphite follower control rod design, which provided operational benefits under normal conditions, created positive reactivity insertion precisely when maximum negative reactivity was needed to control developing instabilities. The accident sequence proved that reactor safety could not be ensured solely through component reliability and procedural compliance if the integrated system design contained inherent vulnerabilities to specific combinations of conditions. The RBMK design was not unsafe due to unreliable components or inadequate procedures, but rather due to information system blind spots that made protective decision-making impossible under conditions that could develop through normal operations. These findings challenged the fundamental approach to nuclear safety analysis, which had focused primarily on component failure modes and external events, rather than systemic failure modes arising from design integration issues. The accident demonstrated that protective systems could create rather than prevent accidents if their design assumptions could be violated under credible operational conditions. The generic lessons from Chernobyl extended beyond nuclear technology to any complex system, relying on indirect measurement for process control. The accident illustrated how information architecture failures could create conditions where operators making correct decisions based on accurate instrument readings could unknowingly commit systems to destructive failure modes. Prevention of similar failures required systematic analysis of the conditions under which diagnostic relationships between measured parameters and actual system states could break down. Control systems needed to maintain diagnostic validity under the full range of credible physical conditions, rather than simply providing accurate parameter measurements under normal conditions. The accident also demonstrated the importance of analyzing transitional regimes where normal operating assumptions might not apply. Many complex systems include operational envelopes, where fundamental relationships between measured and actual parameters undergo qualitative changes that could compromise control system effectiveness. Design approaches that rely on protective measures activated in response to parameter deviations must account for the possibility that protective measures themselves could worsen system stability under specific conditions. Emergency systems designed to provide safety under normal structural and thermal conditions may lose effectiveness or become counterproductive when those baseline conditions change rapidly. The Chernobyl investigation ultimately proved that Unit 4 was destroyed not by equipment failure or human error, but by the systematic operation of systems designed for safety under conditions that exposed fundamental contradictions in the reactor's design logic. The accident occurred because control systems designed around specific thermal-hydraulic assumptions failed catastrophically when operational conditions violated those assumptions while remaining within the apparent design envelope. The forensic evidence established that complex systems can exhibit failure modes that emerge from the interaction of protective measures rather than from the failure of individual components. These systemic failure modes can remain latent until specific combinations of conditions test fundamental design assumptions that are normally taken for granted. Prevention of such systemic failures requires design approaches that explicitly consider the conditions under which protective measures might become counterproductive and that maintain system controllability even when basic assumptions about system behavior prove invalid. The lesson of Chernobyl was not that nuclear technology is inherently unsafe, but that safety cannot be ensured through component reliability alone if system integration creates vulnerabilities to conditions within the operational envelope.